our Unit 7 notes. We're going to start over here on this page. We've done everything so far, okay? Here's where we're at. I'm going to do some notes, and then I'm going to do a little skipping because I need to get to our math equations for today. So that way next week on Tuesday, you can come in and we can be prepped and ready to take that quiz next week. We'll do notes before we actually take the quiz. Okay, first one over here. It says refraction. Hopefully we recall there's a difference between reflection and refraction. Reflection is whenever light hits and bounces off. Refraction is when light hits something, but it continues to travel through it. And then when it does, it's going to bend and change directions. That's what refraction is. So refraction is going to be the bending of the wave as it passes at an angle from one medium into another medium. It says here that refraction occurs when light's velocity or its speed is going to change. Well, why does its speed change? The speed is going to change because it changes through two different mediums or two different densities. So for an example, when you walk down this hallway, you're walking through a medium, which is air. Now imagine if you were in a 5-foot swimming pool. That medium is water. You can't walk the same speed. Look, your velocity is going to change because water is thicker. It's going to slow you down. Okay? The same thing with light. When light has to go through two different mediums, it can either cause it to speed up and go faster. For an example, when light moves from an air medium to a from a faster medium to a slower medium, like air to water or glass, it's going to refract towards the normal line. When light is going to go from a slower medium, like glass, to a faster medium, like air, it is going to refract, but it's going to refract away from the normal line. So what I'm trying to say is I would go back and reread this paragraph definitely before the next quiz. I know Easter's coming up, but you know what? In between egg hunting and whatever your celebration is, please make sure you read your notes this weekend, especially that page. All righty? Jesus is not going to mind if you read a little bit of your physics notes. It's going to be okay. All righty, let's keep going. And like I said, I will start to skip in just a moment. It says here, parts of the refraction. Do you remember that quiz that we took last week? Let me get that quiz back out. Right here. Remember this? This was a picture of the parts of reflection. I promise you on Tuesday, you're going to have a picture, and it's not going to be reflection. It's going to be like this, refraction. Okay? So I wanted to make sure that we definitely know that. So the parts of the refraction, for an example, we have the same thing called the normal line, right? That's this line right here, that dash. It may or may not be a dash, but we know that the normal line is always going to be 90 degrees or perpendicular to the surface. So if this is the surface between the air and the glass, this normal line is perpendicular, 90 degrees to it. That normal line is going to be perpendicular and separate the two different mediums. This is medium right here. This is medium number 1, glass, and this is medium number 2, air. So I can see that light is shining in from the glass, and it's refracting and changing its direction, and it's going through now air. But look up here. Some of the light is showing me that it's being reflected. That's what this line is up here. Okay? Now, from that, we have a couple of new things. We have theta I and we have theta R. Okay? Those are new ones. Theta I is going to be the angle of incidence, which is going to be the angle that is going to enter then into the medium. It's going to enter the angle of refraction, which is theta R, is going to be the one that's going to bend because it had to change. So if you look really close, it's kind of hard to see it, but it always touches the normal line. This right here, it's kind of hard, but I'll write it in. Theta I right here, and this right here is theta R. Okay? It touches the normal line and touches the light. Okay? And then that other line, one more time, it's just reflection. Okay? So let's be prepared for sure to be able to label. Okay? Now, let's go ahead and start our first equation. Equation number 1. For equation number 1, we're going to have the index of refraction. This is an easy equation. I'm actually not going to take much time right now to practice this one, but I will practice it before we take our quiz next week. The index of refraction is n, lowercase n, equals lowercase c over v. Easy cheesy. It's 3 variables. Now, you already know the C. The C is the light that shines through a vacuum. And remember, it's on the formula chart, so you don't even have to memorize it. Here's my formula chart, and here is letter C right here. C is the speed of light, which is 3 times 10 to the 8th meters per second. Okay, now lowercase n is a new variable for you. That represents the index of refraction. And v is the speed of light in the new medium. Okay. Now, one thing that we definitely need to know is that n can never, ever, ever be less than 1. 1 is the fastest thing we know, which is the speed of light. 1. Okay? One more time. N can never, ever, ever be less than 1. I mean, I don't know. Maybe if you time travel, maybe if you go through a black hole, maybe if some kind of crazy scenario or situation. But at this moment, we do not know an n less than 1. It will always be 1 or greater, okay? V, you know what V is, the speed or velocity. V is, for an example, would be right here in the chart. Those are going to be my V's. How fast is it traveling through my substance, if that makes sense? Like my new medium. How fast is it going through there? Alrighty? So I guarantee you, either you would be given that V number or you're going to be given a chart, something like that. But we'll talk about that in just a moment because this formula is going to help you on the next one. The next one will actually do practice problems in just a moment. Let's go ahead and fill in the blanks first. It says that the index of refraction, you can see this, is going to be a ratio, right? A division problem is a ratio. And this ratio is going to be the speed of light in a vacuum over the speed of light in a different medium. What is that speed? Right? It says here, remember that speed of light in a vacuum in outer space is going to be the same as if light was traveling through air. Our atmosphere that we breathe is considered to be pretty much the same as the speed of light through a vacuum in outer space. It's not much of a difference, so we just consider it to be the same, which is still going to be 3 times 10 to the 8th meters per second. So keep that in your mind. Speed of light, which is 3 times 10 to the 8th, is pretty much the same in outer space or here on Earth. Our atmosphere is not that thick, okay? Not like some of these other planets where they have really thick atmospheres. Ours is pretty thin. It says over here that the index of refraction, which is the NR for air, is 1. Now, I'm going to pause for a moment, and I'm going to come to this chart. If you look at this chart, actually it says 1.000293. Okay? Do you see how tiny you have to go to before you actually get, since that is the reason we consider it to be 1. It really is bigger than 1, but it's not significant enough, okay? So we consider it to be the same. The index of incidence, or if it was NI, the index N of incidence, I, for air, whether you're coming from air or going through air, like you're going to go to air, we consider it to be 1. And light doesn't bend. We consider light to still travel in a straight line. So the light from the sun in outer space, when it hits here and comes into our atmosphere, we consider it to still travel and go in a straight line, and it doesn't bend. Does it truly? Well, I guess so, if it's like a rainbow. But if it's not raining outside with all these clouds, well, then it's going to go in a straight line, okay? It says here that a large index of refraction is going to have a slower speed or velocity because it's thicker, it's large, it has a bigger density. A smaller index of refraction is going to have the faster velocity for that light because it's thinner, it's less dense. Light can travel through it faster. So when NI is greater than NR, light bends away from the normal line because light is moving faster through the new medium. When NI is less than NR, light is going to bend towards the normal line because it is moving now slower. It slows down. Again, if I had to give a suggestion, I would probably go back and read this part of my notes. I would probably just reread it a little bit over the weekend. In between egg hunting, and I hope you get a lot of candy this weekend. If not, take your siblings' candy, whichever way you want to do that, okay? But don't do it while they're looking because you're going to make them cry, okay? Do it when they're not looking. When you're ready, we're going to turn the page. Because that equation is literally 3 variables. All you're going to do is plug them in and divide, and you're done. Easy cheesy. But this next equation, which I'm just going to skip down to, some students get a little thrown off. So we're going to write this in, and then we're going to practice this next equation. It says here that NI, what's that NI again? That's going to be do we recall that one? Index of incidence versus NR, the index of refraction. So NI times the sine of theta I we just used theta I last page, equals NR, the index of refraction, times the sine of theta R. Oh, man. Okay, for those of us that was here last semester, we definitely did some sine, tans. Remember those in cosines? Well, here's what I'm going to tell you. Our problem last semester is we had to remember, do we need to be in rads or degrees? Well, because we're using a sine, you might want to put yourself a note. Must be in degrees. You need to be in degree. So please make sure that you're in degree or degree. I'm going to put this degree mode, right? So you need to go make sure that you're in the right mode right there, and you're going to be in degrees. Okay, so I want to make sure that we're all on that same page. Now, let's go ahead and come back over here. NI. NI stands for the index of, oh, wait. Is that NI? Yeah. Of incidence of the first medium. Where is that light coming in through the first medium? Multiply it by the sine of the angle of incidence. Oh, I missed an N up here. And R is going to be the index, because letter N stands for index of refraction, which is going to be the second medium. And we're going to multiply that by the sine of the angle of refraction. And don't forget, the angle of incidence and the angle of refraction always touches the normal line. I can't repeat that enough. Always is going to touch the normal line. Now, believe it or not, this weird equation, which please don't freak out, I promise you it's going to be super easy in just a moment, okay? It's actually called Snell's law. So Snell's law is going to determine the angle, oops, I can't even spell, of refraction. Meaning, how much is it going to bend? How much is it going to refract? Okay? Believe it or not, a lot of diamond companies, they bank on this part. How can I make those diamonds refract more and shine more? You know, what if I cut the diamond this way? What if I polish it a little bit more? What if I do this? What if I set it into the ring a different direction? How is light going to come in? What is light passing through? Air. And then it's going to pass through the diamond. How is that refraction going to look? Is that diamond going to look good? Is it going to be worth the money I want to charge? So a lot of diamond jewelry companies, not just diamonds, but jewelry companies, they really bank on this. They know this very well. It says here that in 1621, Wilbur Snell experimented with light passing through different medias. It says here that he developed the relationship called Snell's law. If you come up with something, you get to call it after you. It says here, which can be used to find the angle of refraction for light traveling through any two different mediums. I don't know about you, but I want to make sure that that diamond is real. How much is it going to refract? Does it look good? Okay. So with that said, I'm going to turn the page to practice, okay? I will go and fill this out and post this part on D2L. I really want us to get some practice in. All right, so here's our two practice equations. From our two practice equations right here, it says, oh, wait a minute, let me write that formula for you. Ni times the sine of theta I equals Nr times the sine of theta R. Remember, that's the equation from the previous page. And do you see this? This is my N values, okay? Remember, the lowest N value I can get is a 1. I can't get any faster than a 1. All right, like I said, I don't know, maybe time travel. But until then, 1 is the smallest number I know. So the Ni and the Nr are going to be one of these numbers because of the medium it's traveling through, okay? Now, the theta is just a theta. It's an angle. It says here that light is traveling, and it has a wavelength of 589 nanometers. It says it's traveling through air. Believe it or not, what have I said? In physics, words have number value. So it's traveling through air. Air is my Ni, or my first substance. It's going to go through a slab of crown glass. So some type of glass that's called crown glass. Nr. Nr is your second medium. And it's going at an angle, a current angle of 30 degrees. Okay, I know that this is a theta, but at this moment, I'm not sure if this is theta I or theta R. Let's keep reading. Find the angle of refraction, question mark, theta R. That's what I want to look for. So this 30 must be my theta I. Does that make sense? I went and I finished reading. So that way I can differentiate who is theta R and who is theta I. Let's fill in the blanks now. It says over here, I'm going to go ahead and do Ni, which is air. Oh, what's the number for air? Don't get me wrong, it's 1.00029 blah, blah, blah. But because it's practically the same as a vacuum, we call it 1. Times the sine of theta I, of 30 degrees. 30 degrees. Equals Nr, crown glass. Use your chart. Crown glass, 1.52. Times the sine of theta R I'm looking for. Make sense? Hopefully. Okay? Now, I'm looking for the sine of theta R. And since this is being multiplied by 1.52, hopefully your brain is saying, hey, Miss Munson, go ahead and divide. Divide so you can cancel out. Divide so you can cancel out. Okay? Calculator. The sine, hopefully you can see my calculator up here. I can scroll in a little bit more if you need to, of 30 degrees equals, divide by 1.52 equals 0.33. I'm going to round up. 0.33 equals the sine of theta R. Completely not my answer. Mr. Houston, we did this. We did something like this. Remember when we were doing like all those projectiles and those angles and stuff, and when we were looking for the sine, the cosine, or the tan, which was the theta, we had to do an extra step. And I'm looking for the theta here. 0.33 is not my answer. I need a theta. What do I push? I know you know it. Do you know?
Isn't it second and then
You're going to let Miss Shelby outdo you. Look, he's smiling. He's like, ah, yes. Oh, she just schooled you. Absolutely. Here, let me write it up here. The inverse, you remember that? Which was the second key sign. So let's hit second key sign, 0.3, and I'm just going to round it up, 0.33. The actual answer is 19.27. The theta is 19.27 degrees. There it is. I know. I can't believe that. I can. Good job. Good job, Miss Shelby. Proud of you. All right, let's do this again. Miss Shelby, how many more siblings? Are they all going to come here too? How many siblings do you have? Just one? She's coming here too?
Probably.
All right. All right. Keep it going. Keep it rolling. Oh, she's going to have some high expectations.
She's a little crazy.
She's a little crazy. Okay, she's a little crazy. All right, no worries. It's going to be fine. I'll have to call home for her, maybe. All right, let's do this again. Okay, let's focus. Find the angle of refraction. Theta R. For a light ray that enters a bucket of water from air. NI is your from. That's your number 1. NR is your water, number 2. Because it comes from air into the bucket of water. If this is my theta R, this is my theta I. Easy cheesy. I'm going to scroll so you can see. There goes the formula. And look at this. I'm looking for theta. Mr. Houston, do not let Miss Shelby outdo you. You need to hit the second key. Don't forget. Let's plug this in. Okay? Ni is air. What's my number for air? I have to just, I can memorize it or look at the chart, but it's 1. And I'm going to multiply that by the sine of 25 degrees equals NR, which is water. Look at the chart. Go find your water number. 1.333. Multiply it by the sine of theta R. Do not forget to hit the second key for the inverse on that, because that's really what we're looking for. I'm going to divide by 1.333, cancel, divide by 1.333. Go ahead, hit that second key. So the sine of 25 equals divide by 1.33, which is not my answer, 0.318. Second key sine, 0.318. The theta equals, hopefully I'm not sure if you can see my calculator. There it is, 18.54 degrees. There we go. All right. Equation number 2. We can finish once we finish 3 equations today. And then we're done. I know. Now, if you look at our notes, we have finished everything else at the bottom. So we can turn the page when you're ready. Okay. When you're ready, turn the page right here. Okay. So let's, I forgot to fill this in for us. Let's fill this in and then we'll get to our next equation and then we are done for today after we practice this equation twice. Okay, so let's go ahead and do that. Let's fill this in. Our focal point, which is known as big F, is different from the focal length, which is going to be my little f. This focal length right here today is going to be part of the equation down here, okay? That's what we're actually going to look for in this equation, the focal length, not the focal point. The focal point was where you were drawing those lines, through, okay? Look at this. Do you remember when we did those drawings and we had those big dots or the big Fs? Those are called the focal points. There's two focal points. The focal length is what we're going to calculate in just a moment. So it says here that the focal point for converging lenses is going to be the location where the image of an object is focused. Like it's nice and clear at this distance. Unlike mirrors, lenses actually have two focal points. Remember when we did those drawings, there was a dot on both sides of those convex lenses because there's two. Now the focal length, which is what we're about to calculate, is going to be the distance from the focal point, which is big F, to the center of the lens. This equation that we're about to do, eye doctors do it all the time, especially for those of us who need glasses. They've got to check to see, okay, where's your focal point, where's your focal length, and where are you producing an image in the back of your eye so you can see those letters that they give you on that chart. It says here both the focal lengths for a lens are going to be the same, okay? The focal length will be the same on both sides. Remember, this converging lens, this convex lens is see-throughable. My glasses are clear. I can see through them. So I'm going to have that focal length on both sides, the front and the back side of my lens. It says, here's your equation. Your equation is going to be 1 over DO plus 1 over DI equals 1 over lowercase f. Focal length is lowercase f. Okay? We're almost done. We're going to practice these two, and then we can call it a day for today, and then start enjoying your 3-day weekend. Okay, so DO, that's our first variable right here. This DO is going to be the distance from object to the lens. Okay, that's the DO. Whoa, okay, we'll look at a picture in just a moment. The DI is going to be the distance from image to the lens. And the lowercase f is going to be the focal length. We just said that in that paragraph above. Okay, now let's come back. Thank goodness for Miss Wadding, who's been amazing. She got her cow eyes, and they were in my office yesterday afternoon. So imagine this is your eye right here. My eye is looking at this pencil. The pencil is an actual object, like a pencil, a pen, a marker. It's an actual object. It's not fake. My eye, and that's what this is right here, this lens is your eye, is looking at it. With light that's shining and hitting it, it's passing through my eye, and inside my eye, I actually have a convex lens, and that's why we're going to cut open cow eyes, so we can see that there's convex lenses inside of them. And on the other side, in the back of your eyeball, all of this light is going to come to one point, okay? And that's going to produce an image. This is the DI. Does that make sense? Because this is the DO, because this is the object to the lens. This is the DI, the image to the lens, okay? So let's go ahead and let's take a glance at this. It says for number 1, an object is placed 20 centimeters in front of the lens. Object, DO. With a focal length, lowercase f, of 12. Find the image location, DI. Okay, I'm going to pause real quick, making sure we know that there's an object, there's an image, and then there's a focal length. Okay? But I want you to take a glance. Do you see the DO and the F are both in centimeters? Leave it. Leave it. When we get our DI answer, it's also going to be in centimeters. Okay? So let's just leave it all in centimeters. Let's don't stress. Okay, here's my equation. DO, 1 over 20 plus 1 over DI equals 1 over 12. Okay, that looks like a pretty easy, cheesy equation. I will say I see fractions. I see fractions in this equation, and guess what? We don't like fractions in physics. Now, the cool thing is that you've got this really cool calculator, and you can do fractions in your calculator. But I don't know, maybe I'm just like really old. I like to take them out of fractions and put them into decimals. You do you. Does that make sense? If you want to do it like I do it and put it into a decimal, then do it that way. If you want to use your personal calculator and make this into a fraction, then put it into a fraction and do the top number and bottom number. It's all up to you. Here's how I do this. 1 divided by 20 equals 0.05 plus 1 over DI equals 1 divided by 12, which is 0.083333. Okay? I need to look for the DI. This is a pretty easy, cheesy equation. So to do that, hopefully you see Miss Munson. Subtract this side for this number and subtract from this side. That way you can get your DI by itself. And I agree with that. So let's do that. Subtract 0.05 on both sides. That gets to cancel out. Subtract 0.05 on this side. 1 over DI equals, subtract 0.05, comes out to 0.333. How easy is that? Oh, 0.2? Oh, absolutely right. 0.0. Look at my screw up, Mr. Houston. I'm so sorry. 0.0. Mr. Houston, I kind of know your math skills. And I'm hoping that you're sitting back there saying, Ms. Munson, that is completely still wrong. Because it is wrong. It is completely wrong still. There's a problem. Back in probably, I don't know, 7th, 8th grade, maybe 9th grade, maybe like whenever you did Algebra 1. So maybe 8th grade or 9th grade when you took Algebra 1. Okay? When you took Algebra 1 and you're looking for an unknown variable, Mr. Houston, could you look, can you have the variable at the bottom of the division? Cannot. But I got to get that variable, do you see it at the bottom of the division? I got to get it up. So here, why don't we just do this? Why don't we flip it, the reciprocal? Oops, hold up. Why don't we just flip it? But wait a minute. If you do one thing on one side, you have to do it on the other side. So this number, how would I flip this number, Mr. Houston? I agree with him. because what he did was he says this every number is over 1. So what he did was he just flipped it. He said if you want to call it over 1, equals 1 over 0.0333. That number doesn't count. Use your cell phone. Give me the real number. We don't like fractions. DI equals 30.03 centimeters. There you go. Easy cheesy. I just think we just needed that algebra skill to know that we cannot leave a variable at the bottom of the division. Let's just flip both sides or get the reciprocal. Again, if you want to just type it into your calculator your way, you do your way. This is how I've always done this for 18 years. One more time, and I promise I will leave you alone. We will call this a day. A pencil. A pencil is an object, so that's DO. It's placed in front of a lens, and it has a focal length of F, 10. Find, question mark, DI. Find the image location. Okay, 1 over 30 plus 1 over DI equals 1 over 10. And remember, they're all in centimeters. Let's leave them in centimeters. Okay? I personally do not like fractions, so I'm going to come over here and I'm going to put them into a decimal, 0.033 plus 1 over DI equals 0.1, I think, right? Yeah, 0.1. I still need to get the DI by itself, so I'm going to subtract 0.033 to cancel 0.033. So now I'm going to end up with 1 over DI equals 0.067. And I cannot be finished because the DI is at the bottom of the division. I need to flip it, and I'm going to flip this one also, because every number is secretly over the number 1. So if I flip this reciprocal, I've got to flip this one also. So DI equals 1 over 0.067, or divided by 0.067. Hopefully you got 14.93 centimeters. So I don't think it was too bad of an equation. I just wanted to